because you cannot solve every problem. There's a lot of problems in exercise. So I will share that PDF file that from each exercise which problems you have to solve later. Okay.
Okay, sir.
So for
So and
yes,
sir.
yes, for this problem, question number three. Okay, after the class you can ask me. Okay.
Okay, sir.
Okay, we'll discuss after the class. Yes. So next, 2.5.
Excuse me, sir.
Yes.
Sir, can you explain once more the multiplication rule, sir? Or the conditional probability of answer?
Multiplication rule. Okay, so this is that was followed from the definition of independent events.
Yes.
So not sorry, independent events. Sorry, that is
It's a dependent one, sir.
conditional events. Yes. Conditional probability. Okay, that is probability of a by b equals to. I've seen this probability a by b equals to probability of a intersection b divided by probability of b. Okay, and also probability of b by a, that a has already happened. Then the probability of the event b is again probability of a intersection b divided by probability of a. Okay. So from this, the multiplication rules follows. That is probability of a intersection b. You can write from the first relation. You can write this as probability of b into probability of a by b. Okay. And for
Yes, sir.
second, also you can write probability of a into b. This thing. This was the multiplication rule of the probability of a intersection
Yes,
b.
sir. That I know, sir. But in a question,
Yes.
sir, it is not given directly, no. So we means probability of B. We can find then probability of B. Probability of A when B has occurred. So then, how will you find probability of A intersection B? In the question, it is not simply is given that probability of A intersection B is
No,
this
no.
or that. So
If it is given, if you want to find this, suppose you have to find this probability of intersection B.
yes,
The
sir.
same question it should be given. Otherwise, how we find this? Should be given probability of A by B.
No, sir. In a question means blood group is something like that given or the DVD player. So in that it is not given. It is given that the means manufacturing or the repairing here is this and this. So can I share, sir? Can you explain this, sir?
That should be given. Yes, you can say.
Okay, sir. Sharing, sir. Sir, is my screen visible, sir? Sir, this one, sir. This question, sir. This example, sir. Hello, sir.
Yes, yes.
Yes, sir.
This
So this example, and so I understood that the above one, sir. This I got it, sir. The means the blood group one. But sir, this is I'm not able to recognize this
chapter
question,
two,
sir.
right? Chapter two, 2.4.
2.4, sir. Yes, sir. 2.4.
Yes, yes.
And sir, the state means the statement has been given. It has not solved the, all the statement has means the solution is given in this statement. So
Yes, yes.
statement form.
Okay, so for this question, you claim that the conditional probability is not given. Then how to find this intersection, right? Are you asking for that?
Yes, sir. Sir, the question I'm not getting, sir. Sir, this question, sir. So means the 50% of the brand one means it has been given three different brands, 30% and the 20% of brand two and three respectively. Then it is given that the 1 year warranty for and the part and the labor charge is given, sir. 25% and 2010 for the first and third. So, but here in the question number two, what is the probability that the randomly selected means purchaser has the DVD player? What will need repair while under warranty? So, what is this? So because the question number one and the two, it is means relatively same.
Okay, actually, I have not seen this problem earlier. Okay, let me see this problem first, then I will discuss. Okay,
Okay, sir. Okay, sir. Okay, sir.
is it okay? Yes.
Okay, sir. Thank you, sir.
The next point five event. So when we say that the two events A and B are independent,
So when the probability of it doesn't depend over the that of the B.
that is the probability of one event does not depend on the occurrence or non-occurrence on other event, right? Then we say that the two events are independent. If the probability of one event does not depend on the dependent occurrence or non-occurrence of other event, then we say that the two events are independent. So mathematically, two events A and B are independent if probability of A intersection B, this equals to probability of A into probability of B. If probability of A intersection B equals to probability of A into probability of B, then we say that A and B are independent events. Okay. And they are dependent otherwise. Now we can derive from the conditional probability for other relation for these independent events. Suppose probability of B not equals to 0. Suppose we assume that probability of B is not equals to 0. So then probability of A by B, suppose you want to calculate then probability by A by B. Okay. So we assume that A and B are independent and this uh, probability of B is not equals to 0. Then from the definition of conditional probability, probability of A by B, this equals to probability of A intersection B divided by probability of B, right? Then we say that Then probability of A intersection B is probability of A into probability of B. Since probability A and B are independent, so you can write probability of A intersection B equals to probability of A into probability of B divided by probability of B. Okay, so this equals to probability of A. So that is probability of A by B. This equals to probability of A. Okay. So see this, if A and B are independent, then probability of A by B equals to probability of A. That is, the probability of this event A does not depend on the occurrence or non-occurrence of this event B. So this is the independence of the two events A and B. So for to check the independency of these two events, you can either check by this one, that is the probability of A intersection B equals to probability of A into probability of B. Then you can say that they are independent. Also, you can use this probability of A by B equals to probability of A. Similarly, probability of A not equals to 0, then also probability of B by A is equals to probability of B. For example, okay, can you give an example of this independent events A and B?
Yes, sir. Tossing all the 2 points of getting
Tossing.
head.
What is the event A and B in tossing two coins? You have
Sir,
to
if you
define
take
this two
head, then
event A as
sir, getting head, sir, when it is tossed.
and B, event B.
When the means,
So yeah, your event A and B should satisfy this condition. Then we say that these two events are independent. Okay, so can you give an example? You take the
so
random
can
experiment
be
tossing two coins. That's right. Now you have to define A and B, two events.
so can be getting of at least 2 head or at least 3 head when the two coin is tossed.
Yeah, for two coins or at least three are not possible. Only two, at least two. Well, maximum two. That is
At least 1 head. Sir, it can. Yes, sir, at least 1 head.
okay. For this, you take the same. Okay, take the same random experiment that is tossing two coin. Can you define any events A and B? Can you define these two events A and B so that their probability of A intersection B this equals to probability of A and probability of B. This. Then we say that A and B are independent.
So
So
finding
tossing
when
the
the
tossing two coins, how many outcomes in there? The sample space?
sir of two coin it will be four.
Two into two, four. Four. Yes, four. So head or tail or head or head or tail. So can you define now the event A and B so that probability of A into probability of B equals to probability of A intersection B?
So then finding means the probability of A can be given as to the means head, and the probability of B can be given to be the tail. Means the B has occurred. Means the tail has already been declared. So, can it be?
Sir, it can be that the event of the appearance of tail or head on one coin is independent of the appearance of tail or head on the other coin.
Okay, so if we define A is getting only one head, okay. So if we define this on head, then what is the probability of A?
2/4.
2 by 4. It is half. And getting on tail,
Sir, same, so 2/4.
on tail is also probability of B. This is half. Okay. So in this case, probability of A into probability of B is 1 by 4. So if you find A intersection B on it and on tail, there is
Then it will be 1/4. So,
1 by 4.
sir means probability of intersection B, it will be 1/4.
What will be in A intersection B in the outcome? Can you define this?
Sir, might be so 1/2.
Actually, you have to define this A and B. So that probability of A intersection B equals to probability of A into probability B. Can you define this? A and B an event from here. Okay, for example, I will take another example, then you can see this. Then what is how you define? Suppose rolling a dice. Okay, if you define A is odd numbers, okay, and B is multiple of 3. Multiple of 3. Then in this case, A and B are independent or not? Can you check? Because in this case, the total number of outcomes in rolling a dice 6. That is 1, 2, 3, 4, 5, and 6. Okay, so A odd numbers. Odd numbers means 1, 3, and 5, right? And B multiple of 3. That is multiple of 3 means only 3 and 6. So if we find this probability of A, total probability of A, uh, number
So
of outcomes at yes, number of outcomes in A, that is 3. Total number of outcomes is 6, that is half. And probability of B, number of outcomes in B, that is 2, divided by number of outcomes in total number of outcomes, that is 6, so on by 3. Okay. So what is probability of A intersection B?
so 1/6.
A intersection B, see this, what are the outcomes in A intersection B? A intersection B means A and B both are happening here. So
So only 3.
yes, odd numbers and multiple of 3. So odd numbers and multiple of 3, that is only 3, one element. So this is 1 by 6 probability of A intersection B. So hence probability of A intersection B equals to probability of A and probability of B. So this implies here A and B are independent events. Okay. So can you define similarly here two events A and B, so that probability of A intersection B equals to probability of A into probability of B.
Sir, A can be getting at most one head and B can be getting at most one tail.
Okay, if you define this, getting at the first is getting at most one head.
Yes, sir.
Okay, and B is getting
At most one tail.
one tail. So at most one head means there two possibility are also there here. A. So 2 by 4. The probability is same, 1 by 2.
Yes, sir. So then
Getting
B of A intersection B will be 1/4.
getting at most one tail also 1 by 2. So A intersection B is getting at most one head
And
and
get
at
P
most
of A
one tail.
intersection B is means A intersection B is getting at most one tail and one head. Then it is coming TH. So then also it is HT also.
HT, yes.
Yes.
This also will be HT. So this is again 2 by 4. So this is half. So in this case, actually probability of A intersection B, this is not equals to probability of A. So they are not independent events here. Okay. So next for three events. For three events, So for three events, we use two terms for independent of events. Three events. One is pairwise independent, another is mutually independent. Okay. What is this? Three events A, B, and C. There, three events A, B, and C. They are pairwise independent if probability of A intersection B, this equals to probability of A, probability of B. That is, they are independent pairwise. Okay, so probability of A intersection B equals to probability of A into probability of B, and probability of B intersection C is probability of B into probability of C, and probability of A intersection C, this equals to probability of A into probability of C. So three events A, B, and C are said to be independent, pairwise independent. Sorry, pairwise independent if these three conditions are satisfied. Okay. And and they are called mutually independent. Mutually independent if mutually independent if they are pairwise independent together with one more condition, that is probability of A intersection B intersection C equals to probability of A into probability of B into probability of C. That is, three conditions must be satisfied of this pairwise independent. That is, probability of A intersection B equals to probability of A into probability of B, probability of B intersection C, this equals to probability of B into probability of C, and probability of A intersection C, this equals to probability of A into probability of C. Okay, and one more condition is probability of A intersection B intersection C, this equals to probability of A into probability of B into probability of C. So three events A, B, and C are mutually independent if they are pairwise independent, and probability of A intersection B intersection C, this equals to probability of A into probability of B and probability of C. So if these four conditions is satisfied, then we say that they are pairwise independent. If this only three condition is satisfied, then we say that they are if the past three condition is satisfied, means they are pairwise independent. If all these four conditions is satisfied, that means they are mutually independent. If any one of these three condition in pairwise independent events, if at least if one condition is not satisfied, then we say that they are not pairwise independent. For example, for random experiment, of rolling two dice. One second. So for the random experiment of rolling two dice, uh, define the following three events. A is the event that first die is a 1, 2, or 3. One, two, or 3. B is the event that first die is a 3, 4, or 5. And C, first die is a, and C is the sum of two faces equals 9. Equal 9. So now we have to check are these three events A, B, and C, they are pairwise independent. Mutually independent. So for the random experiment of rolling two dice, define the three events, the following three events. A means first die is a 1 or 2 or 3, and B is the first die is a 3 or 4 or 5. And C is the event that sum of two faces equals 9. Then are these three events A, B, C pairwise independent? Are these three events mutually independent? You have to check one by one. Okay. The first check for pairwise independent. Uh, for this, you have to find what is probability of A, probability of B, and probability of C. Then probability of A intersection B, B intersection C, A intersection C, like this.
So
So what is
probability are 1 by
A?
2.
Yes, 1 by 2. Because if you write this total number of outcomes, that is the sample is is like 1 comma 2, sorry, 1 comma 1. So rolling two dice means there are 36 outcomes, 1 comma 1, 1 comma 2, up to 1 comma 6, then 2 comma 1, 2 comma 2, up to 2 comma 6. Okay, dot dot, 6 comma 1, 6 comma 2, up to dot dot, 6 comma 6. There are total 36 outcomes. Okay. 36 outcomes in the sample space. Probability of A. So what is the event A? A means the first die is 1 or 2 or 3. Okay. So first die is 1 means this plus there are six possibility that first die is 1, that is 1 comma 1 1 comma 2 1 comma 6. Okay, similarly first die is 2, there are six possibility again, that is 2 1 2 2 up to 2 6. For 3 also there are six possibilities, that is 3 comma 1 3 comma 2 3 comma 3. So first die is either 1 or 2 or 3, there are 18 possibilities, 6 plus 6 plus 6. That is, so probability of A equals to number of outcomes in A, that is 18, divided by total number of outcomes, that is 36, which is half. Similarly, probability of B, again this the first die is 3 4 or 5, so again 6 plus 6 plus 6, 18 outcomes in B. So this is 18 by 36, again half. This is, now what is probability of C?
Sir, 1 by 9.
Yes,
Sir,
yes.
sir, none of these are pairwise independent but is mutually independent.
No, no, pairwise independent. If they are not pairwise independent, then obviously they are not mutually independent. Okay, so I think because this, if you see this definition, the first two definition here. So pairwise independent mean this three condition must be satisfied. Okay, and mutually independent means this four satisfied. Okay, so if pairwise not
Okay.
independent means any one of these three events, three conditions is not
Yes.
satisfied, so they obviously they are not mutually independent.
Yes, sir.
Yes, yes. So they are not pairwise independent and they are not mutually independent. Because here, if you see this two conditions, so mutually independent, this mutually independent, this implies pairwise independent. That is, if three events are mutually independent, then they are automatically pairwise independent because the conditions of three pairwise independence already contained in this definition of this mutually independent. Okay, but the converse may not be true. If they are pairwise independent, then may not be mutually independent. Okay. So here probability of A equals to half, probability of B is half, probability of C. So C means here the sum of the two faces equals to 9. Okay, so what are the outcomes in the event C?
Sir, 3 6 4 5 5 4 and 6 3.
Yes. So if you see the outcomes in C, that is the sum of two faces equals to 9. So this is 3 comma 6, okay, 6 comma 3, and 4 comma 5, and 5 comma 4. So there are four outcomes in the event C. So probability of C equals to, this is 4 by 36, that is 1 by 9. Okay. So if we find probability of A intersection C, so probability of A intersection C equals to, what is probability of A intersection C? Can you find probability of A intersection C? We define these three events. Huh?
1 by 18.
Uh, A intersection C. A means the first die is 1 or 2 or 3, and C means the sum of the two faces equals to 9. So A intersection C means first die is 1 or 2 or 3, and the sum is 9.
1 by 36.
Yes, only one possibility, that is 3 comma 6. The first die is 1 or 2 or 3, and their sum is 9. So only one possibility, 3 comma 6 in the event A, in the event A intersection C. So probability of A intersection C is 1 by total number of outcome, that is 36, 1 by 36. Okay, so this equals to, obviously this is equal, this is not equals to probability of A into probability of C. because probability of A is half, probability of C equals to 1 by 9. So probability of A intersection C, this is not equals to probability of A into probability of C. So this implies A, B, and C, these are not pairwise independent. So hence you can say that A, B, and C are not mutually independent. Are not mutually independent. Although this last condition of mutually independent is satisfied. And check this. That probability of A intersection B intersection C is equals to probability of A into probability of B into probability of C. This condition is satisfied because if you find this probability of A intersection B intersection C, so this is equals to I think 1 by 36.
Yes, sir.
Yes, and probability of A into probability of B, probability of C is also 1 by 36. 1 by 2 into 1 by 4, 2 into 1 by 9, that is 1 by 36. So although it is satisfied, but they are not mutually independent because these three events not satisfy this condition. Probability of A intersection C not equals to probability of A into probability of C. So they are not mutually independent. So see one theorem that if A and B are independent, then show that number A complement and B complement are independent, and B A complement and B are independent, and C A and B complement are independent. So if A and B two events are independent, then A complement, their complement, that is A complement and B complement are also independent. A complement B are also independent. A and B complement are also independent. So we have to prove this. It's very easy to. So given that since A and B are independent, and from the definition of independent of two events, we know that probability of A intersection B is equals to probability of A into probability of B. Since A and B are independent, it is given. Now you have to show this A complement and B complement are independent. So for this, we find this probability of A complement intersection B complement. If probability of A complement intersection B complement is probability of A complement into probability of B complement, then we say that these two events are independent. So let me find this. So probably from a set theory, you can write this as A union B, the whole complement. Okay. So this equals to 1 minus probability of A union B. You can write this because probability of A complement equals to 1 minus probability of A. So this equals to 1 minus next probability of A complement A union B. This formula is probability of A plus probability of B minus probability of A intersection B. So this equals to 1 minus probability of A minus probability of B, then minus probability of A intersection B. Now since A and B are independent, so we can write this as probability of A into
So
probability
that
of
will be plus.
Yes, sir, it
yes
will be
plus yes plus minus minus plus. So this okay. So this is 1 minus probability of A. The from the last two terms we can take this common minus probability of B. So this is 1 minus probability of A. Okay. So this equals to 1 minus probability of A into 1 minus probability of B. So this is 1 minus probability of A means probability of A complement, and 1 minus probability of B means probability of B complement. So we get this probability of A complement intersection B complement equals to probability of A complement into probability of B complement. This implies A complement and B complement, they are independent events. So similarly, you can prove this last two parts also. This is homework. You have to prove this part B and part C. Okay. So these results you have to also remember these results, because using this result you can solve the problem from the exercise. Okay. So in next class you will solve the problems from this 2.5. So I'm taking attendance, roll number 101,
Present, sir.
119,
Present, sir.
148,
Present, sir.
165. Okay.
Present, sir.
165,
Present, sir.
205,